the orchestration of this entire thing, and communicating with the user, and managing your long-term memory, and deciding how to. So there are so many things. I treat this as an AI system or an AI operating system that is very tied to the resources that actually run, at least in some use cases when you actually run the models and not just call APIs.
Hi everybody, welcome to another YAAP episode. And today I'm here with our CTO, Barak Lenz, who's going to talk about...
What are you going to talk about?
Yeah,
what are we going to talk about?
I asked you for framing about this, and I really want you to repeat what you said to me.
Well, I don't think there's a one-liner that could summarize what we want to talk about. So I'm not sure what's the best intro. We could start by just diving into things that are already established in the industry and then go from there. But I don't know. Maybe once we're done, we'll know how to do the intro.
Yeah, so I want to say I'm really excited to have you here. I think that you're one of the most fascinating people I've ever got the chance to talk to. And every time that I have the time to sit with you and hear what you have to say, the vision that you have or like the problems you identify, I found very unique. I found these are things that not enough people are talking about. So maybe give us a brief introduction about yourself and let's dive into those problems.
Yeah. So I'll make the intro really brief. I'm not that interesting. So name is Barak, also called Baraki down here at AI21, 42 years old. I've been programming since I was 8, working in startups since I was 16. So that's 26 years now. And the past, 14, 16 years I've been a CTO. The last 8 of them, the CTO at AI21. So I've been here since day one, was in charge of training all our models, our systems, everything. And I don't know, here we are. I guess that's enough intro. So,
everybody has a story of the way you interviewed them. And now I finally have a story of that time I interviewed you. So very pleased to be.
My interviews are interesting. We'll talk about it in another podcast. I can talk about the gist here. The gist is to ask you things there's no way you could have prepared to, because people prepare more than I would have liked to interviews. So you want to get a glimpse of the real person, you're going to have to be more creative than just come up with, interview questions. You need to really try to talk to the person, and that's not trivial to do. So
hopefully anyway. I can Barakify this interview with you.
We'll see.
So let's just dive in. No one-liners, no framing of this. What do you think is interesting right now in the AI industry?
So I'll start speaking about how current leaderboards are reporting results, and then we'll take it from there. So if you look at some of the popular, let's say, recent leaderboards that came out, things like ArcAGI, Sweetbench, Deep Research, or the more complex things that usually people would say that agents are in charge of executing. So what's being reported now is the best average score across the entire data set. That's the leader of the leaderboard. And also they're reporting usually dollar cost. And these dollar costs can be very steep to some use cases, right? So for Sweetbench, it could be, 70 cents for the leaderboard. But for ArcAGI, it could actually be $40 to $80 per instance. And what's being reported right now, again, is who's the best on average and what is the average price. So let's start by talking about how we could have looked at it differently and why we should look at it differently from the perspective of AI systems, of us being able to run a lot of things, not just being able to run one thing. So the first gap that I want to talk about, I think, is a gap that's already been addressed both by the industry and any literature. You usually have 2 names assigned to it. I'll stick with one of them. So one of them is the Oracle gap. The other is the validation gap, but I'll explain what it is in very simple terms. It's the difference between my success at one, so how good I am on average, and how good I could be, my success at, let's say, K different rollouts. And again, this is a very known phenomenon that models have a better success at K because you're sampling from a distribution. So if you go back to papers like R1 or big model releases, sometimes they report success at K for some things. And it's important to say that even the best agents today and best reasoning models have a much better success at K than success at 1. So there's a gap there. So you can say, let's refer to SweBench, for example. You can get 75 at 1 to be on top of the leaderboard. But your success at 64 is actually much higher. It could be something like 87, 88.
Which makes sense, right? If you do more tryouts.
Yeah, but this is why I call it the validation gap. So if I had a validator that as good as the Oracle, if I knew when the answer is right, I can actually close this entire gap. So I could be in the leaderboard, but score, the success at K.
You mean that if I would run K times and I have the validator who can choose the best one every time?
Right. So this is why it's called the validation gap or the Oracle gap. The way that we do it is we validate, but the validate can have a gap from the Oracle. So for some problems, this gap is very solvable. I'll just give a toy example. If my problem was generating a really big prime number, then I would say models are probably not perfect at doing it. But there's no problem in being perfect at validating this, right? You can just run a function that's called isPrime, and it will be as good as an Oracle. So in a use case like this, I can actually be as good as my success at K. And actually current leaderboard holders in a lot of benchmarks are actually doing stuff like this. So they're doing generation, and then they're doing one of two things, either only validating, that means the input is a candidate to be an answer and the output is whether it's good, or they do what I would call a reduce function, meaning they get a lot of different candidates and they pick the best one. So you can call it reducing or re-ranking depending on whether or not you synthesize a new candidate out of the existing K candidates, or you're just picking one of them. But current state of the art in a lot of the leaderboards are doing something like this, right? And the validation can be either something very strict. So in Sui, it could be, make sure you ran all your tests and you passed the tests that failed at the starting point. But it could also be a very soft validation. It could be running a complex array of models doing judgment in order to build up a validation function that will try to mimic an Oracle. So let's say I'll have like grounding tasks. The way that the leaderboards are actually evaluated are value functions like this. They're judgments, but you can develop better value functions compared them to Oracle. And again, in verifiable data, the Oracle is very, very clear. In less verifiable data, the Oracle is usually just a validation function. So this is the first gap. I think it's established. I think if I go back, I think when I read AlphaCode, which is a great paper by Google, I don't know if I would call it underrated, but I think it was underlooked at the time. They really showed that you can do very complex things with actually old models like T5 3B, which is considered very much obsolete today. But if they tested it with million generations, the success would still rise. So you actually talk about success at 1 million. Right?
That's kind of like the first test time compute scaling.
Well, they didn't do test time compute scaling, but they did something really cool. So they generated a lot of candidates, and then they used embedding models to cluster them and then pick a candidate out of every cluster. And they did something very complex, but the gist of it was pretty much the same. They did some pruning, which is a validation, make sure the code can run and stuff like this. And then we're actually able to show that they're able to, downsize 1 million to like 10 candidates, and the success at 10 on them was amazing at the point, right? And they talked about, I think, Olympiad questions like people talk about now. So right now we're doing them at success at K that is much smaller, but the gist of it is the same. And actually the way we train models to be better at success at 1 is doing GRPO usually, which actually does exactly this. It does K rollouts, and assuming you had some good rollouts, it's able to say, this is better than the ones that are not good, and it pushed the model to a better success at 1. But as I was saying earlier, you will never get to a perfect success at 1 at any task. You can maybe get perfect at, 2-digit addition, but you're not gonna be perfect. So there's still a very big validation gap. This is one of the things that AI systems need to solve. So you can solve it again with a simple loop as generate and validate, and if you have a perfect validator, but you can do way more complex things like majority votes or run a lot of different things, find different ways to compare them, reduce them, etc. But your goal should be very clear. There's a gap between successor 1 at K. We want to close that gap and be able to deliver the user the successor 1, which is actually the best we could have done.
I do want to mention something. You keep saying AI systems. It feels that we're now, the industry or the world evolved to talking about AI agents. You don't believe this is the case because it's much broader?
I think an agent is a problematic word. I can say an agent, let's take different examples. For SweBench, I would say an agent is actually a very good name. It's coding, but the thing is that I need to give it like a Git mini branch to run on. So it actually needs an environment. The system that runs it can't be called an agent. It runs a lot of calls to different agents. So I would call it a system, an AI system. Each trajectory in the system can be done by an agent, right? And maybe you can say the entire system is an agent on its own. But again, I found the word agent very confusing. What type of agencies do I have? What kind of... When I think about agent, I think about things interacting in the real world. So again, the SWE agent is really an agent. But a lot of times, agent is just a general name for a multi-step thing being done with an LLM. I find it ill-defined. What if I switch LLMs between steps? Am I still an agent? How is my agency manifested, right? So I'll call the SWE agent an agent, like the React loop that tries to solve a SWE problem. But the system running it and trying to optimize success at K out of several runs, that's not an agent. That's an external thing to the thing. So anyway, just to clarify your question about AI systems. But again, I'm not the best guy in terminology. So I feel like when you say agent, you can be very, very misunderstood because people are using it as a buzzword to splash around things. But for me, agency is a real thing. There are, in classical AI, there are multi-agent systems. It has a very crisp, clear definition. And agency means you have knowledges and beliefs. And so I'm not going to go dive into this. I'll just try to use agent less than maybe most people. But again, I don't mind.
AI systems. I'm cool with that. Just wanted to understand more.
Cool. So we talked about the first gap. Again, I'll call it the validation gap. I think it's the most well-established one. And then I'm going to go into more nuanced gaps. And for them, I'm going to use my names. They're not necessarily the best names, but let's try to see that we're crisp on them. So again, summarizing validation gap, the gap between my success at 1 and my success at K. What an oracle could have done if he had a perfect oracle. The second gap that I want to talk about is what I like to call contextualization gap. So what does that mean? So right now when you report a leaderboard, you're reporting, and I said this briefly, the best on average. But I would claim that once you're an AI system, you're not a specific thing, you can do whatever you want, then you can actually have a lot of different things that you could have done. So the contextualization gap is actually the gap between what is best on average and what is best at every input in my leaderboard. So let's say SweBench, just as a running example, has like 500 examples in the verified. Right now, the top of the leaderboard is whoever does best on average. But if you look at who does best on each example and include costs in this, you can draw a huge gap between this best one, which is usually very, very expensive, right? Because it needs to be best on average, and the best on every instance. And at every data set that I've looked on, there's a big difference in difficulty, even within the data sets that's supposed to be the same. So actually, much older models and much cheaper models could have solved a lot of the problems. That's one side where you could have saved. You could save a lot of costs. So an example would be, GPT-5 Pro would get something like, 72, 3, 4, 5 on SweBench. But GPT Mini would get something like 60 with a almost perfect overlap. That means that I don't need to use the bigger model for at least 60%.
So 60% of the examples you can just use GPT Mini.
Right, and I'll get the same result.
But the question is, how do you know which ones?
This is why I call it the contextualization gap. So if I had it, again, imagine an oracle that for every input would allow me to pick the cheapest thing that gave a good value. So there are actually two gaps between that and the best on average. One of them is the cost. And the other is, the best on average did not necessarily succeed in all the examples that everyone else succeeded on. And actually, again, if you look at SWE, the best at one, when you run it even 64 times, it still has inputs that are not answered by it, but are answered by other rows in the leaderboard. Let's put it like this. So actually, if you looked at this contextualization gap, and I do think we could show data about it. I don't know how you attach it to the podcast, but this gap is huge. So you could have, if you had a contextualization oracle, do it with less than 10% of the price and actually get a better score. But again, assuming I would have known. But when you actually do a drill down of the leaderboards, it turns out that it's not necessarily that hard to know, because the easiest questions are pretty much always solved, or the success at 1 and K gap is very narrow, which means you could have known very quickly that this is an easy problem and picked an easy thing. And there's actually another edge to this, and these are the two hard examples. Then maybe you just don't want to even try them if you knew they were too hard, because empirically no one's successful in that.
Maybe it's a weird question to ask, but like you're mentioning, you could have known that these are the easy examples. You can know it right now because you're looking at the success rate in the leaderboard. Do you have any way to know in advance? Like you have a classifier that says this is an easy problem?
I wanted to just present problems, not necessarily solutions to this. The solution to the contextualization problem is what I would call an action model, but I'm not sure we want to deep dive into this, but you could say that this is a task to a model. Some people would say just the most basic thing to do is test this with a router. Try to train a router to route the easy things to the easy and the harder things to the harder one. But I do want to build up on what we've done. So if you imagine that I do have a validator, from the previous slides, right? So then I could actually maybe run a lot of actions on every input and also be able to get correct answer in places that the best on average didn't. Right. So again, there are two ways for me to improve on this imagined Pareto curve of what I could have done. I could have done it much cheaper if I knew where to choose the cheaper, but I could have also chose other very expensive methods for these inputs that are not really solved. And assuming I have a validator that's good, you can imagine me, not just running the best one, but running an ensemble of all the best ones in order to get better answers. But that would be up to my appetite. Do I want to do it cheaper, or do I want to squeeze more? So the way I would look at the execution of this would be like an anytime algorithm that's able to spend whatever budget you give it. And then if it's a low budget, the focus is, what's the cheapest thing that could do it. But if it's a big budget, the focus is, what are the different things that I could have done? So if you look at it in a contextual way, you're actually building a portfolio of different things that you want to do, not just one. Because if you pick just one, you can't move really much in the Pareto curve. Well, actually, in reasoning models today, you can put effort level, right? But this is just the tip of the iceberg. So it shows you that the industry is going places. But again, you have effort levels for, again, let's stick with GPT, for all the different models. And there's I think 300 or 100 times cheaper, the GPT Nano, right? So even if I just choose one model family, there's a huge space of spending and values. And if you look at it as a portfolio, there's also a huge gain to get by using different things. So you see it as an anecdote today. People say we did interleaving steps of Claude and GPT and did a state of the art on something. But more principally, if you chose the right thing to do in a contextual way, there's a huge gap here to solve. And so assuming this contextualization gap is understood, we could.
Yeah, you did mention the word portfolio several times, and which I'm not entirely sure I understand what you mean.
So I think what I mean is, right now, when you look at the leaderboard, you can just pick one thing to do, right? So the top of the leaderboard could be, I'm using Gemini Pro with React Sui agent and, running it. This is what I would call my action. This is what I do. But if, again, you look at the contextualization gap, maybe that action, which is best on average, can be complemented by others. And there are actually scientific ways to build portfolios that have diversity. So the gist of it is you're going to look at the internal correlations of the action. You can say my portfolio should be different things that I could do that complement each other, either in terms of cost or in terms of value.
So,
right? And they would end up building me portfolio. So you can imagine my portfolio at SweBench would be, I don't know, GPT Nano, GPT Mini, GPT Pro, Claude Opus, and I don't know, Grok 2. And right? And each one in a contextual way is better for some things, or they're better as an ensemble. Right? So I end up with a portfolio of things that I could pick on, and given a contextualizer, I can pick the right thing, and I can start seeing where I am in that contextualization gap, which again, as I mentioned, is huge. So this is an algorithmic problem. In the validation problem, I need better verifiers. Here I need a better way to contextualize in order to start closing this contextualization gap. And I end up with a portfolio of actions that my system can choose from in a contextualized way.
And just to make sure that I fully understand, so the portfolio includes a lot of different actions or models I can use, but it also means that I have to have some sort of either orchestration or an action or something like that, that since I have a portfolio, I also need something to choose which one to do.
Well, in the simplest case, all you need is a validator, right?
And run all of them.
And then you run all of them. That would just give you better performance. But obviously, you'd pay a lot.
Yeah.
So this is the most trivial thing we can do. But yeah, once you have something to contextualize, again, in the simplest case, it would be a router. In the more complex case, it would be something that really tries to evaluate the chances of success and the costs for the different action, and in an intelligent way run this according to budget. Right? And then you really, I think you can get why I'm talking about AI systems, because there's a piece of code driving here that looks at the budget, looks at the costs, and try to optimize this Pareto curve, which is very different than calling an API that trained on trajectories that try to mimic the exact same thing, right? Because again, the trajectories weren't trained on the same success at 1 basis success at k, right? Does that make sense now?
Yeah, it makes
all right.
a lot of sense. So we talked about validation gap.
Yeah.
We talked about the
contextualization
gap.
Gap.
Contextualization.
Again, that's my name. I'm not necessarily, but
maybe
maybe there's a better
name that
name.
will stick.
Maybe we'll see.
So what's the
Are we
next
ready
gap?
for the third gap? We are.
I'm ready for the fifth
So-
gap.
Yeah. So the third gap. Here is a little bit more tricky to define the oracle, but I'll try anyway. So the third gap is what I would call the latency gap. So the latency gap is the difference. The theoretical difference is between the shortest latency I could solve a problem in, but this is just a theoretical boundary. I think more practically, I could say it's the difference between the shortest solution that I have and the average solution that I have.
When you say solution, you mean something that solves
Something that actually solves. So if we
it.
talk about, so again, let's, for an example that GPT Nano can solve something, let's say with the same token budget as GPT Pro, it would have a lot of latency gap because they take very different times producing tokens.
Both of them give the same solution, but one is faster, significantly faster than the other.
Right. So a very simple way of showing this is actually by running things in parallel with a validator and early termination. When you do this, you can say I'm running several things in parallel, but once one of them is finished and is validated to be good enough, I terminate all the others. So again, this is a way of you to chip into this latency gap, right? I want this faster, so what I'm doing is trying different things but again, this is the really, really, really first fundamental thing that I can do. But if I try to reason about these different latencies and had an execution strategy that tries to minimize the latency, maybe I can do much better, right? So, and again, when you draw this gap, there's a huge gap. Right? If you look at different reasoning models trying to solve the same problem, and you look at the shortest good answer that you'll find, and the average one, I think it's at least 3 times the number of tokens on average, again, on hard problems. But this is just scratching the tip of the iceberg, because again, if you look at this and combine this with contextualization gap, if I could do the same on a much cheaper model with less steps, this is where my latency couldn't be, right? And if you look at AI systems that are older and not use LLM, things like Stockfish that plays chess, you can see that it can check a lot of different situations very quickly, where an LLM, if you would do it like you do it today, if LLMs play chess, they only do it in depth, right? Either a reasoning model, spitting out a lot of tokens, or so your minimum latency is huge, and it could have been much smaller, right? And one of the reasons is that at least right now, current state-of-the-art systems do not really parallelize, right? And again, even if they did, it would be on the full trajectory. So again, if we stick to the SWE as a running example, if I run like something like a mini SWE agent, I can do early termination and save, let's say, 3x sometimes. But this is just tip of the iceberg, because I did the parallelization in a very primitive way. Anyway, so this is the latency gap, and I think it's a huge gap that's I think sometimes misunderstood, right? Things like deep research show very cool performance, but a lot of customers and a lot of use cases do not want to wait 30 minutes for this to work. And again, we're just in the beginning. The tasks get more and more complex. In tasks like MLE Bench, you actually give the agents 24 hours to complete. Maybe sometimes in use cases you can wait 24 hours, but just put it all together. The time you wait with the total budget that you've spent and maybe failing in the end, you gotta treat latency as a principal component. So I think if I were to change leaderboards, the second thing I would say is don't report me just total cost. Report total latency as well, because this is what's gonna get this use case to the market, at least in a lot of use cases.
Total latency, I think, right? We know that, for instance, a model, like let's go simplistic. Let's say a language model with X number of parameters, you can use different GPUs, right?
So your little way of deciding on pricing, what's usually being done today, pricing and latencies, is just looking at list prices of models. And yeah, I agree that it's hard to calculate. It's a very hardware specific thing. It gets even more complex if I actually tell the model to generate a few answers at the same time. If I pass the API with num results greater than 1, I'm actually spending less than I spend when I just generate 1 on average out of these rollouts. So I'm not saying it's trivial to calculate, but you could calculate it very empirically, right? And then see what the latency was, and then say, well, this is the latency on this setup. And again, one of the reasons I call this AI systems is this setup has a lot of things in it. You need to be able to use different models. You need to be quick about it. You need to be able to give them timeouts and retries and a lot of different things in order to make this entire thing work. But again, the point was to establish that there's a gap. There's a big latency gap. Just as an example, GPT-OSS is pretty good as a reasoning model of doing short trajectories compared to other reasoning models. So if you compare it to a lot of different reasoning models, it would do the same task with way less tokens on average. So you could say it's better on that sense. And again, I think most customers care about latency as a first principle. If you can't get back to me within whatever it is that an SLA would give me, then I don't know if I can use you. Does that make sense?
Yeah, I think it's a shift that we're seeing recently, and keep me honest here. I felt that the thing that people care about the most is quality, and that was mainly in the POC era, I would say,
Right.
where people like, I don't care about cost, I don't care about latency, I just want it to work. And
Yeah.
now, as the industry adapts more and more AI in there,
Mhm.
we see that the quality is kind of there in a lot of things, and now the
Yeah,
latency
but
starts
at
to.
least in some things,
Yeah.
the quality is already there. But again, it's not just dollars. This is what I'm saying. So again, dollars are already appearing in some leaderboards. But if you don't always consider latency as a different dimension of the cost. And again, it's very different than dollars. Because if I wanted to optimize for latency, I would run tons of things in parallel. But if I wanted to optimize for cost, I would never run anything in parallel. I'll just run one thing, validate, another thing, validate until I'll get the right one. So you can actually get very, very different execution strategies if you prefer latency over cost. So that's one of the things that an API of current AI systems should be able to give you. Not just how much do I want to spend at, low, medium, high, but also, do I want to do it in parallel? Do I want to do it sequential? Do I care about latency or cost more? Or maybe a balance between the two. So that was our third gap, the validation gap.
No, this was
the latency gap.
gap.
So we talked about the validation gap, success at 1 versus success at k, contextualization, best on average and best on every instance in terms of value and cost in two dimensions. And then latency gap, the gap between how much does it take me to solve this on average and how much it could have taken if I did the shortest thing. And now we're going to talk about the 4 gap, which you may say it's about bringing all of this together, and explain why the gaps are even much bigger than what we've shown so far. So I would call the 4th gap, I don't know if my naming is good here, but I would call it the decomposition gap. Because right now, whatever the problem is, when you feed it to a model, it treats it as a single problem. Again, this generally, you use what people refer to as agents, and they don't tend to parallelize. You can parallelize them externally, like some leaderboard candidates do. But again, you're not really parallelizing things that are happening internally. So again, if we stick with SweBench, that means that when we talked about the latency gap, all I could do is the gap between, the shortest SWE solver that did it in 20 steps compared to, 100 steps that it takes on average to solve this. But if you look at the problem fractally, meaning if you were able to decompose and look at the 3 gaps that we discussed so far and say, at any given point in my React loop or whatever my running system is, I would have been able to say, what are all my options? Choose my entire portfolio for this. What is my best option for each step? And if my best option is still not good enough, maybe I need to run a lot of them in parallel in order to get one of them right. But do this all the time. Not just do it externally on these huge agent blocks that people use, but be able to do it at any given point. Say, do I want to fork myself and then continue in several ways? Do I want to really use the expensive model for every step, assuming I chose it? Or are there only several difficult steps that made me think the bigger model will do better here, but I don't need to use it everywhere, right? So if you look at this and say, I was able to really decompose, you'd be able to get into this agent and at every decision point, look at the contextualization gap and the latency gap and be able to parallelize and choose the best thing for each step, then these gaps explode. So I talked about, saving like 10x if you chose like the simplest thing that worked on SweBench. But if you're really able to at each step choose the best thing and able to parallel, then what is currently being done looks like a pretty weak baseline, I would say, right? Because it's always very, very long in latency, not very predictable in terms of what I'm going to get. It can fail. And again, I'll find out that I failed very, very late, right? It would take it a long time to fail. Yes, so these were the four gaps that I wanted to talk about, and I just want to stress out that they're really important in training time as well. In training time, you'd usually say, well, I don't have a portfolio of actions that I can do. I'm trying to just train my model. But if I can't, for example, take care of the latency gap, and I want to do K rollouts and then do gradients on them in GRPO, that means I'll need to wait for the slowest one. And when my SME agent can do 200 steps for nothing, that means that each reinforcement learning step on this SME agent just takes a long, long time, right? And then the bigger the K is, you pay more in these rollouts. You're willing to pay, but you pay for the latency of the longest one, right? And then you can start doing some heuristics, do more rollouts than you wanted, but it means that because these latencies are so huge, you're kind of progressing very slowly in the reinforcement learning as well. So it's not just at inference time that I want to do this. If I don't do this in training time, my training is going to be, and the longer the task I want to give my agent to run, the more this latency gap and is important. And if I was able to decompose and put everything together, it would be way smoother, but very different.
I think in this day and age, if you will not do it during training time, someone else will solve this problem, and there will be 3 new problems until your model will be finished training. So it's interesting. I didn't think about that.
I think the infra for top labs today of how they do the rollouts in GRPO is much stronger than people think. There's tons of effort into exactly how to do the rollouts in an efficient way, and they're trying to squeeze time because you're using a lot of GPUs in the setup, right? It's a very expensive setup. But there's a reason people are still doing React and reasoning models. The reason is that its decomposition is hard. Because when you're doing React or a reasoning model, everything is in the context. You don't need to ask yourself, am I passing enough context to this subproblem? So to be able to divide a problem into subproblems, you need to pass context in and out. And it turns out to be very tricky. So I think this is why things are still being done like that. But again, if you ask me, predict the future on that, there's no way that we're going to continue doing everything depth first. This is how it looks. So everything that's being done today is depth first. If I want width as well, I'm doing it externally. But if I fractally thought about it, like a real search problem does, like an MCTS, break this into width and depth and really think about the different values that you can get and understand that there's a huge portfolio of things I can do. And there are more and more models coming out every day with different features, different costs, different latencies. You will want an AI system that intelligently looks at the different options that it has and in a contextualized way chooses the best thing according to the user preference, right? Because again, latency and costs are like apples and oranges. I can't really squash it into one variable. I need the user to tell me what he wants, right?
Yeah, and they're also, I think, different size of the trade-off, latency and cost.
Yeah, at least to some extent, right? There are different trade-offs. You can say that they're also coupled in sometimes. The bigger the model, it has a bigger cost and a lot of time bigger latencies. But there are different things to optimize. And I would do it very differently if you told me, I have time, but I don't want to spend much. Or you would tell me, I have no time, throw everything and the kitchen sink in it and see if something sticks. So this is an execution strategy of an AI system.
Well, I think we talked a lot about gaps up until now, almost exclusively about gaps and the problems. I want to hear from you. I don't know if to call it solutions, but maybe approaches how to solve that, or like where do you see things going forward, or what are you working on here about that?
So let's start with each gap and how you solve it as a baseline. So validation gap, the baseline is just a validator or a scoring function, right? It's something that maybe I've verified with humans offhand, or it depends on how I want to do it. Again, if I'm doing self-judgment or running code. But I think this gap is well understood. right now. So if you look at state of the art at ArcAGI, what they do is actually treat the problem as a code problem, and their validator is making sure that the code that's been written works on the examples. ArcAGI has 3 examples for each input. So in that case, their validator is almost as good as an oracle, assuming there are no errors in the data. So you're just able to close the validation gap, and then you spend a lot of compute, and you're state of the art in the. So you don't need to, in that case, develop an LLM at all. They just used existing LLMs, but they just did a good validator. They saw that the same code should work on all of them because they're examples of the same problem. So this is about validation gap. Again, contextualization, the baselines are routing. But the approach that we're taking is very different. We're actually using models to estimate values and costs, and then use an execution strategy that's actually a code that does the decision making according to these priors about value and cost. And I don't want to dive too deep into this. Maybe we could in another podcast, but it's actually a model that gets the context, knows the different things that it can do, and knows how to estimate it. And again, the simplest baseline for this would be use the average from the leaderboard. But as I was saying, it's very different, and you want it to be input dependent. So this needs to be an LLM to do it in input dependent. I'm not going to talk about implementations, but again, I think the first thing people need to do is draw that gap.
Just to make sure, not talking about implementation. Mm-hmm. When you talk about this type of model, what I think about is when DeepMind released AlphaGo, right? They had this value function at each step of the MCTS. Well, something like this? Or?
But here is different because the assumption in an MCTS used to be, and I think it doesn't work right now, that every action or everything costs me the same amount. So I'm not reasoning about the costs, I'm just reasoning about the values.
Yes.
But as I mentioned before, I think there are very different ways to optimize this, and the cost is super important. And again, it could be 1,000x different costs between the most expensive model out there and the cheapest model out there that could still do the task for you. So I think it's a more rigorous approach to really calculate these values and costs or estimate them, and then run a search that uses these values, right? And again, the reason not to use something like an MCTS is the fact that the cost is very, very, very different between the things that I can do. Again, if you just look at GPT Pro high reasoning level to GPT Nano low reasoning level, I think there's 1,000x gap in the cost. So I could do it like an MCTS and ignore the cost. I just think that's very faulty, right? So if you estimate the cost, you can actually say things like, I can't do it for you in time, and be way more humble about what you can do. Where you estimate values, you estimate cost. You can also say, I don't know if I know how to answer your question. I think one of the reasons that agents and models usually try to answer today is you're never punished in the leaderboard for not trying. But if people dived into costs and latencies more, then not trying to answer is sometimes the best thing to do. If I were to ask a model to try to solve the Riemann hypothesis to me, I think it would be pretty foolish to try to solve it. And maybe these cases have been somehow handled by model makers, but the more general case is not. So there are problems in Sweetbench that I haven't seen any model solve, but they still try very, very hard, and maybe they're not solvable and they're buggy in some way. I think a real estimation of values and costs is way better than saying, I'm going to choose the best values, which is what an MCTS would probably do, right?
Yeah.
And these value functions needs to be contextualized. So you can think of me running an LLM, and then I have the problem that this has a cost as well. I need to consider this cost. And again, there's a reason these things are not yet, very, very...
It becomes more complicated the more that you add more.
But when you look at the gaps that I've described, you'll see why this has to be done, right? Because the gaps are so big that it's worthwhile doing this heavy lifting and try to get this to work. And again, I think this is where things are headed. So I think the best coding applications today already decide about different models, already do parallelization sometimes with reduce or validate, and they use Git mini branches, and they do a lot of the things that I've described. But you could say that every use case needs to be like this, and the decision should be more rigorous. It shouldn't be, we've tested, and these kind of problems tend to be solved by a small model, and this kind. You need to do something way more robust with the contextualization problem. But I think you're starting to see this emerging, but there's not yet a general framework that does this in a rigorous way. And this is where we're heading, right? Something that solves these three gaps and is able to really decompose. So you can imagine I would want a system that I could tell it solve the entire SWE bench. And it needs to understand that it needs to parallelize to every exercise, and for each one, maybe do the same thing. So right now, these things are done externally. But if you are recursive about this decomposition, you can actually get very good priors from your action model about what's going to work and what's not going to work. So it ends up that if you look at it that way, it's not that you can just save way more than you could without doing this decomposition. You could actually get way better scores as well. But again, there are difficulties in this around context management and memory and things like this that the reasoning models and React Loop just, they don't need to take care of because it's always one huge context. But again, you need to try to remember that latency is not linear in sequence length with attention, right? So you're even paying way more than you would have wanted. The more steps you take, each step costs more. But it doesn't necessarily depend on the entire past, right?
Yeah.
So if you're able to tease it apart, then your jobs become.
Yeah, that's actually something that I've encountered before, that a lot of agents, specifically in deep research agent, but I'm sure coding agents as well, that a lot of the work is done for context management. The realization that you don't really need the entire context and like trim a lot of it to save in context, in tokens, in latency and cost.
So I think the main thing here is moving from heuristics to a principled system that does this as a principal component, right? And if I'm able to parallelize as one of the things I can do in my portfolio, and I'm able in a contextualized way to see when this is the best thing to do, then I should be able to do parallelization in a principled way, right? Because if you can't parallelize, it would always fail, right? If you need the context to pass, you're not going to get any value. But if you don't, that's always going to be way cheaper, right?
Yeah. Let me ask you this. I know you don't like to predict what will happen in the future or something like this.
I did algo trading for too long. I'm willing to predict seconds to hours, and that could give me good values. But any prediction that's over days is usually mainly standard deviation. But we can try.
No, so I will not ask you for a prediction per se. What I will ask you to maybe guess is from those three gaps, because the fourth one is just a combination of all three, I would say. Which one?
But it's the biggest gap, that's important to say. Because again, if in deep research and in long trajectories, if you're not able to parallelize, you can only save a certain amount. But if you are, again, the difference between stockfish playing chess and an LLM playing chess is how much you could really get, right? A real MCTS search that parallelizes all the time when it needs to, and something that just tries some moves and then decides after a few thousand tokens, usually. There's a huge gap there. Anyway, go.
Yeah. No, but I mean, the fourth one is kind of combining all three. What I want to ask you, from your perspective, what would you say is the first gap that will be closed from the three that you mentioned?
I think to some extent the first one is being closed. The fact that models are good is because they have verified data in the RL for the GRPO. That's one way to solve it. I have an oracle and I train the model basis oracle. It doesn't solve the inference problem, but it gets it closer. And I also have the same for training. So if you want to, train grounding, you don't really need, examples of what is good grounding. You need a good value function. And these value functions are usually an ensemble of judges. So actually the way you train it right now already closes the validation gap. You just don't usually use it at inference time. the same thing. And you don't usually publish this for someone else to see. But if you look at Anthropic, I think they released Bloom recently, which I really liked. You know, they did very complex judgment about very complex behaviors of agent. It only had scaffolding for that built with humans, but the value functions was actually, you know, asking models, is this harmful? Is this, you know, is this agent out of line in a lot of different ways? And it's actually not a bad way to do it. So these value functions that people are using right now, they're already closing the validation gap. I would just say that in some problems, in theory, you can close it completely. I talked about prime numbers. Some problems are easily verifiable, you know, NP versus P, and some problems are way easier to verify than to solve. And for some problem, maybe the validation gap can't be closed because I'm as good as my prior. You know, you know what I'm saying? So I don't know what funny means. I know I've got the funniest model on average, and all I can do is call it, and maybe there's no way for me to improve. But I can say that whenever I tried it, you could do a validation function that closes at least some of that gap. But again, it also has costs. And this is why everything needs to look at the cost in a principal way. There are no free lunches here. You need to be very specific about what you want to do, how you want to do it, and how much it costs. So validation gap is already being addressed. Contextualization gap, there are leaderboards about routing. In a way, they're talking about this contextualization gap. Right? But I think the thing is all about bringing it together. Right? Same for latency gap. Coding models do things in parallel and do sometimes do early stopping when one of them is done. But the thing is doing all of these things in a principled way for every problem and realizing this is the same problem over and over and over again. You just need a good verifier, a good contextualizer, understand when you can and can't parallelize, and again, use decomposition too. So I think all of these things, in a way, it's like I said about alpha code before, you know, people that were doing alpha code probably understood this validation gap long ago. But I think it takes the industry time to understand because, again, the client cared only about value at some point, right, the customer, and then they start caring about costs and about latencies. And I think eventually all of these problems they're already tackled today. 100% doing the RL step of models, right? All of these things are important. There again, contextualization, not so much, but you do train different models. So, so I think we're headed there. It's like eventuality is that all of these gaps will be addressed, and future AI systems would have an anytime flavor and would care deeply about costs and values, just like humans do. You know, I think what I described is a general framing of how you should solve things, right?
Yeah.
It doesn't matter what the problem is. You know, you wanted to do a podcast. There are different actions you could take, right? There are different people that can do it, and they have different costs. You know, convincing your CTO to come has certain costs.
One of the hardest tasks I ever had to do, I have to say, but it was worth it.
Maybe you're not doing hard enough tasks so far. Right?
And maybe I will ask you the toughest question that I asked so far. Now that you spoke a lot on all those gaps, I will ask you again, how would you reframe this episode? How would you...
Well, so yeah, I would say it's about AI systems because you need to orchestrate this. You need to be aware of your resources. So either AI systems or AI operating systems, because once you understand, you don't just do like an instruction. You don't just fire something and forget about it. This needs to be managed. Think just about early termination. Someone needs to understand what are all the things running, what are the dependencies. When we do decomposition, we actually end up with DUGs, right? Directed acyclic graphs that some steps are dependent on others. So the orchestration of this entire thing and communicating with the user and managing your long-term memory and deciding how to... So there are so many things. I treat this as an AI system or an AI operating system that is very tied to the resources that actually run at least in some use cases when you actually run the models and not just call APIs. It needs to know how to, provide safe environments so you could do things in parallel. Coding is one example, but even if you wanted to use a DB, you can't just parallelize infinitely, right? There are resource constraints. So you need to be way more aware about everything. So again, for me, these are AI systems or AI operating systems, and they could run things that you may call agents, right? But they run a lot of them, and they orchestrate them, and they manage them, and they kill them, and they, create new ones, and they do whatever they need. And we didn't even start talking about long-term learning and how these systems can be used to further improve once you've done your production use case. Once I've seen how good I really am, and actually am able to really get feedbacks from people using it, then we start entering a new loop of continuous improvement that this AI systems can give you, either by training things, making the actions better by looking at signals, or just enriching the portfolio, looking at past experiences and learning from them about how to behave in the future. So again, this thing, I see it as a very structured thing. And this is why I call it AI systems.
Cool. Well, thank you so much. It was so interesting learning from you on this. And
thank you.
Stay tuned for other episodes of YAAP.
Thanks, guys. We did it. I can go.